Okay, we're going to talk about the material from the fourth chapter now. In this course, the course breaks naturally into three parts: the first two chapters, then the third and fourth chapter, and then the remaining chapters five, six, and part of seven. And we're working on the part in the middle now, the three and four. And the three and four are the part where the ideas of the course really come out. These are the part where a person, it's really critical for a person to pay attention to what's the big idea. I understand that there's a lot of kind of manipulating things and putting things into stat key, this kind of stuff, but it's critical to pay attention to what the idea behind the manipulations is, because it's much harder to understand how to do the manipulations unless you understand why you're doing the manipulations. Okay, anyway, time to start in. So we're going to do statistical tests. So the setup is I'm back at that Holiday Inn in Kansas City, and I have a doctor who did a study about headaches with the new drug and showed up to present the results that there's a previously unreported side effect from this drug. And the issue is whether the doctor's findings are whether the doctor's findings are easiest to understand as just simply that they got a way off sample, or are the doctor's findings easiest to understand as that there's a genuine effect, there really is such a side effect. Okay, so of course the doctor in front of the room is contending that there really is a genuine side effect, but the people in the audience, the fellow professionals who are willing to be persuaded, but you have to persuade them, they start off by thinking that this is just routine sample to sample variation. If you got a number that's different than the expected number, then that's only because sometimes samples vary. Okay, so how does the doctor convince the audience member? And again, audience member is a fellow professional who's skeptical but will be persuaded by actual evidence that the findings are significant. So to understand where to put the numbers into stat key and all this, a person needs to understand how the argument has to go. So this is how science works. Arguments are not about pottery throwing. They're not about dirty tricks. They're about supporting what you're saying with data. So to win the argument, the doctor has to say something like this. Yes, it's true. Samples vary, and I don't claim that my statistic is the population parameter or the census number. I'm not claiming that the number I came up with is exactly right. We're not in fifth grade. We know that doesn't happen that way. But my p hat, my observed percentage of people who took the drug and reported a headache, is very different than the percentage of people who did not take the drug and report a headache. The chance of getting a p hat like mine by luck, by bad luck, is very small. And then the doctor has to produce the calculation. Because the chance is so small, it's easier to believe my report is due to the drug than it is to believe it's due to routine sample variation. Okay, so that's how the argument has to go. So the actual sort of instances of those arguments as we move through this section are all variants on exactly what was said. What you see is that the doctor here is arguing against the possibility that it's routine sample to sample variation. So routine sample to sample variation is kind of the default, and the doctor has to say, no, my experiment makes it very hard to believe that. Okay. So our central concern here is the possibility that the doctor, just by happenstance, got a sample that's far from the population number. If we're standing there holding a sample, we're holding an X bar or a p hat or maybe an R for correlation, then what we're arguing about is whether that the difference between the X bar and the expected number, or the p hat and the expected number, or R and the expected row is there are two possibilities. One is that it's just a samples vary things. Sometimes you get a p hat that's a little different than the population number, and there's nothing to get excited about. Or it can be symptomatic of a genuine underlying phenomenon. In the case of this doctor, that the drug really does have the side effect of giving people headaches. All right, so let's do a sort of experiment from start to finish. So I'm going to do an ESP experiment, mostly because nobody ever asks me what do you mean. So I'm going to do an ESP experiment where we bring in a subject and they guess 100 coin flips. So we bring in a subject and they get 58 of them right. That's 58. That's kind of a lot. We say to ourselves, I wonder what we got here. So there are two possible explanations. There are two points of view to explain the difference between 58 and 50. So what's called the null hypothesis, the sort of default assumption is there's nothing of interest here. This person's chance on any flip is 50-50, just like everybody else's. And the explanation for the difference between the observed p hat of 0.58 and the expected of 0.50 is just that it's routine sample to sample variation. It is nothing. Nothing has been proved here. That's why it's called the null hypothesis. The alternative hypothesis is that there's a genuine phenomenon here. We don't think that this person's number is 0.58. That is, if we tested this person not 100 times, but 1,000 or 10,000 times, we don't think we'd come up with 0.58. We don't think that the sample number is necessarily the census number, the population parameter. But we think that the difference between the observed 0.58 and the kind of nominal 0.50 is so large that it provides strong evidence that this person is not a 0.50 person, that this person has ESP. This person is not a 0.50 person, and if you were instead tested this person with 100 million coin flips, that they'd come up with a number different than 0.50, this particular person. Okay, so the null hypothesis and the alternative hypothesis. The null hypothesis is the people in the seats at that Holiday Inn in Kansas City. The alternative hypothesis is the person in front of the room, the person making the claim, claiming that there's something happening. In symbols. So I'm going to repeat the claims from the prior slide, and then I'm going to write them in symbols. I know you can read, but I'm going to write them in symbols. One of the things that folks have trouble with sometimes in this class is translating the kind of word problem into symbols, so we're going to work on that. Okay, so the null hypothesis, I'll remind you again, this person's chance on any flip is just like everyone else's. It's just 0.50. The difference between the p hat you observed and the expected 0.50 is just simply due to routine sample to sample variation. I varied the wording a little bit just because sometimes it helps a person to hear the same thing said in 4 or 5 different ways. It just helps you keep track of what's happening. The alternative hypothesis, the contention that there's a genuine phenomenon here, is that there's a genuine thing happening here. We don't think this person's true number is 0.58, but the difference between 0.58 and 0.50, this person says, the difference between 0.58 and 0.50 is so large that claiming that 0.50 is the parameters is hard to believe that. Okay, so here's those two assertions written in symbols. You see that the null hypothesis is written with the symbol H sub 0. The alternative hypothesis is written with the symbol H sub A. You see those colons there? The colons are very important. These are contentions. It's two people having an argument. One person raises their hand and says, I contend this. Another person raises their hand and says, I contend this. So H naught, I'm announcing what H naught thinks. Here, I'm announcing what HA thinks. So when you read H naught is saying, this person, I know they got a high number on your experiment, but I think if you did it in the long run, they would just get 0.50 like everyone else. So this person's true census number is 0.50 like everyone else's. That's what this paragraph says. What this paragraph says here is no, this person's true census number population parameter, if we could test 1,000, a million flips, would prove to be bigger than 0.50. This person genuinely has ESP. That if we could test them with a million flips, so that we knew their number, it would be bigger than 0.50. We're not children. We don't think 0.58 has got to be the right answer, but we think that in any event, it's there. This coin flipper's number is bigger than 0.50. Okay, and again, writing these in symbols and reading other people's symbols gives some folks in the room trouble, so we'll work on this as a specific skill. In particular, sometimes when you're working on learning something new, it helps to learn what's wrong. So I put down 3 common errors here so that a person can right away not get into a bad habit. First error, second error, third error, these errors are all wrong. Don't make them. Okay, first, do you see it says H naught equals 0.50? That's not right. H naught is an assertion. That would be like if you had John say something and Mary said something and you said John equals. No, that's not right. John says that P equals 0.50. So H naught equals, that's not right. HA greater than, that's not right. So H naught and HA are assertions, they're claims. Okay, here we go over here. H naught and HA. P equals 0.50 and P equals 0.58. So this person here is confused. This person thinks that 0.58 is the claimed true number. That's not right. The alternative hypothesis is not a child. They're not in fifth grade. They don't think that if you run a sample of size 100 that you're sure to get the right number. Instead, they think that the 0.58 is so different from 0.50 it provides evidence. So this is wrong because the HA's contention is not that the true number is 0.58. It's rather just that the true number is bigger than 0.50. All right, and then the last error. P equals 0.50 and P hat equals 0.58. This is the error that bothers me the most because one of the big lessons of the course is that we do not care about the sample. So we're not arguing about the sample. I mean, come on, we went out, we took the data, we did the division, we know what the sample is. So we're not arguing about what the sample is. We're arguing here about what is the population number. So you should never see a sample symbol in here. It should always be a population symbol. These two should always be the same. And there should always be colons here, not equals. Okay, anyway, now we get to the sort of the meat of the matter, how the argument goes about the coin guesser. So we have the two folks, we have the folks in the seats and we have the person in the front of the room. So the folks in the seats say, the skeptical but fair-minded, they're willing to be persuaded if you can provide them with evidence. Skeptical but fair-minded folks in seats say, look, samples vary. Unless your sample is really far from 0.50, and what I mean by really far from 0.50 is it has only a very small chance of being there by happenstance, of being there by luck. Unless your sample is truly far from 0.50, then we'll be unconvinced. I mean, we're going to ask you for more evidence than you're providing us with. And we'll just find it easier to believe that your results are due to routine variation than to assume there's something new in the world. So that's what the null hypothesis people are saying. They're saying, look, the default case is that it's routine sample variation. You've got to prove it otherwise. The alternative hypothesis, the person in front of the room at that Holiday Inn, argues against the null hypothesis and does it in a way that we already went over once. We're going to go over a number of times because it's the key idea in this chapter. So the person in front of the room argues something like this. They say, suppose for the sake of argument that you're right, that this coin flipper's true population parameter is 0.50, and the only reason I got a p hat that differs is because we took a sample, not a census. If instead of 100 coin flips, we did 1,000,000 coin flips, we wouldn't see that anomaly. Suppose you're right. The alternative hypothesis says to the null hypothesis, suppose you're right. Well, we'll calculate the chance of getting a sample such as mine. We'll calculate the chance of getting a p hat of 0.5 or more. 0.6, 0.58, 0.59, 0.6, 0.61, but we'll calculate the chance of such a sample. And the calculation's on the next slide. We're, of course, going to use Stackey to do that. In claiming that the difference is just a sample thing, we're going to find that this is what the alternative hypothesis person is claiming. We're going to find that chance is very small, and so in claiming that the difference is just a sample thing, you're asserting that I'm reporting something that had only a very small chance of happening. That's hard to believe. Okay? So it turns on how small a chance there was of getting such a p-hat. So we have to calculate that chance. So of course we're going to use Stackey, and of course I'm going to demo here what a person has to do. So I'm going to bring up Stackey. Come on. There we go. There's Stackey. I'm going to bring down the slides. So I'm going to bring up Stackey, and if I can get the darn thing to work, there we go. And we see we're working on the hypothesis test chapter, so this is the right column. And we happen to be working with a proportion because we're figuring out the percentage of times the person correctly predicted the coin flip. So we're looking at this. Click on it, comes up. So I'm, of course, going to edit the data. It comes up with dog matched with owner, but I'm going to edit the data. And what did my person got? 58 out of 100. Isn't that right? Out of 100. 100. Oh, no, hit the wrong button. 100. There we go. Okay, and you see it says over there, 58 out of 100 is, of course, 0.480. The null hypothesis, we just went over that a minute ago. The null hypothesis is that p equals 0.50. If you need to edit it, you just click on and you enter 0.50. It happened to come up that way, but anyway, I showed how to work it. Okay, so what's going to happen here is that Stackey is going to give me a sampling distribution, and I'm going to get some idea how crazy a sample is 0.58. Is it wildly crazy, or is it perfectly everyday? If it's wildly crazy, then that should persuade the null hypothesis people. If it's perfectly everyday, then the null hypothesis people will remain unconvinced. So I could hit all these buttons and demonstrate all kinds of stuff, but I'm just going to generate 1,000 samples and look at what we're looking at. Looks a lot like a bell curve. It's centered at what is the, there we go. It's centered at what is the null hypothesis. So we assumed that this coin flipper's chance of getting the coin right on any one flip is 50-50. So Stackey generated many samples. Let's just pick on one here. I'll let my mouse hover here. So for this one here, you can see that the sample is 54 out of 100. And for this one over here, you can see that the sample is 43 out of 100. And for this one here, you can see that the sample is 49 out of 100. So Stackey assumed what the null hypothesis people assert is correct, that the true percentage is 0.50, and generated 1,000 samples. So this is as though we had 1,000 people, each of them with a 50-50 chance on any one flip. That each of them flipped 100 times. So I can fill up the chapel with 1,000 people, each of them coin flipped 100 times, and I say to people, okay, tell me what you got for a p hat. And this person here tells me they got 55. This person here tells me they got 43. This person here tells me they got 50. Okay, so is 0.58 crazy, wild, unbelievably far out, or is 0.58 perfectly everyday? So let's find out. 0.58 is greater than 0.50. That was the alternative hypothesis was that p is greater than 0.50. So I click on right tail, and it comes up to some number that I'm going to have to change. So I change it to 0.58, 0.58. That's called the cutoff. And now Stackey has a bunch of dots that are bigger than or equal to 0.58. It colored them all red just to make it graphically easy to see what's happening. And it counted them. What Stackey counted is that that's 78 out of the 1,000, total of 1,000, 78 out of the 1,000 dots. So there's about a 7.8% chance. So let's think again about what's happening here. Big picture. The person in the front of the room is contending that 0.58 is an extraordinary data point. What we found is that 0.58 is not really an extraordinary data point in the context of the null hypothesis. 0.58 is not really an extraordinary data point, that in fact, something like 7 or 8% of the time, that's what you'll see. So if I have that 1,000 people in the chapel and I say, anybody here get bigger than, get 0.58 or 0.59 or 0.60 or 0.61, a lot of people will raise their hand. 7.8% of the people will raise their hand. So it's not an extraordinary, you got to believe me type of data point. Instead, it's perfectly ordinary. Okay, let's go back to the slides. Of course, I put all the screen captures in the slides because a person can go back and look at them easily. There we are. I generated 1,000 samples. The 1,000 samples I generated last time and the 1,000 samples I just generated a minute ago, of course, slightly different. I asked Stackey what's the chance of getting a 0.58, so I clicked on right tail and then I clicked on the button that's down here and entered 0.58. Don't enter 58, enter 0.58. And then Stackey again comes up with the red dots, all the dots greater than or equal to 0.58. And Stackey calculates whether that's an extraordinary, rare thing or is it perfectly everyday. 0.60, now I got 0.78, this time Stackey got 0.60, but it doesn't matter because neither of them is crazy, wild, way off. What we find is that a sample like this is not perfectly everyday, but it's not super rare either. If we had 30 people in the room and flipped the coin, each of them flipped the coin 100 times, maybe one person, maybe two people would get a sample like this. That's perfectly ordinary in the sense that it wouldn't persuade me there was something wrong with the coin flipping. So this number here, 0.60, or what I got in when I did a 0.78, is called the p-value. So we would say that the chance of such a sample is 0.06 in this example, or in my example, 0.78. We would say the p-value is 0.06. So that tells you, because the p-value is not very small, that the null hypothesis people are going to say, this doesn't persuade me about ESP at all. You're going to have to do better than that. So the null hypothesis people remain unconvinced. The alternative hypothesis people has failed to win. We fail to change our mind about the null hypothesis. The technical jargon is we fail to reject the null hypothesis. Okay, one example is not enough, so let's do a second example. So this time we have a person got 81 right out of 100, so it is really a far out p-hat. And we're going to calculate how often would you see a p-hat of 0.81 if the census number were really 0.50. Would that provide really much stronger evidence than the 58 out of 100? Okay, so I'm going to set it up, it's 81 out of 100, so I'm going to set it up again with stat key, get rid of that and bring that in, set it up again with stat key, and now I'm editing the data to say 81 out of 100. 81 out of 100. Generate 1,000 samples. Again, there's 1,000 dots there. Looks like a bell curve. Pretty good expectation of what's happening here. And now I'm going to say right tail for 0.81. 0.81. 0.81. So following the steps I followed last time, except with an 81 instead of a 58. And look at that. There are no dots out there. We flipped the coin 100 times. We performed that experiment 1,000 times, and nobody got numbers anywhere near 81. 81 out of 100 flips would be a truly extraordinary event. 81 out of 100 flips would have a p-value that is essentially 0. So small, stat key was unable to tell the difference between the number I got and 0. Okay, so what's happening there? I'll just click, I'll click through here. This, again, I just like to capture it in the slides for a person who wants to see them frozen. Is you get 0.81 is a sample so rare that stat key's unable to tell it from 0. It's basically impossible. So that's compelling evidence against the null hypothesis. The null hypothesis people say, we think you got your 81 just by happenstance. And you say, no, look, there's practically 0 chance of getting it by happenstance. So the null hypothesis people would say, I guess we were wrong. The technical jargon is you reject the null hypothesis. Okay, so the plan. There are 3 things involved in doing hypothesis testing. You have to get a sense of the argument. I just did a couple of examples of trying to get the sense of the argument. You have to be able to state the hypotheses with symbols and read them when they're stated to you by someone else. And finally, you have to make the arguments, including doing the calculations. So far we focused on 1 because it's hard to understand the other parts if you don't have some sense of the argument. We next are going to turn our attention to part 2, and then after that we'll do part 3 in a variety of contexts. The key thing here, though, I can't overemphasize, is that the mistake that people make when they're doing this is they forget about the sense of the argument and they try to think, oh, you just put that number there. It's so much easier to be able to do these questions if you understand why the parts work the way they work. In addition, understanding why the parts work the way they work will really pay off in Chapter 5, Chapter 6, Chapter 7. They will make Chapter 5, Chapter 6, Chapter 7 very easy. So it's really worth it to every time you do a problem here in Chapter 4, ask yourself, do I understand why I put this number here, sort of thing. Okay, so reminder of the sense of the argument. So you have the doctor at the Holiday Inn in Kansas City. The doctor has to convince the audience members, people in the seats, fellow professionals who are skeptical but willing to change their mind if you provide them with evidence, to reject the possibility that the observed difference can be accounted for by routine sample-to-sample variation. So the doctor has to convince them to change their mind to reject their former point of view. And the argument has to go somehow like this. The doctor has to say, my p-hat, my observed percentage of people who took the drug and reported headache, is very different than the percentage of people who did not take the drug and report the headache. The chance of getting a p-hat like mine, just by happenstance, the doctor has to say, is very, very small. Here's the calculation of that chance. Here's the calculation of the p-value using stat key. It's got to be very, very small. And the doctor then turns to the people in the seats and says, in our field, we agree that experiments with a p-value of less than, say 5% are significant. Because my p-value is less than that, you should think it's easier to believe that my sample report is due to the drug than it is due to routine sample-to-sample variation. And the 5% just varies from field to field. In one field it might be 5%, in one field it might be another number. So the doctor has to come up with a p-value, a chance of the doctor's sample of being very small. 1%, 1/10 of 1%, 1/100th of 1%. If the p-value is 1/1000th of 1%, that's pay dirt. The doctor really got a good result. So just to have rounded through here the different definitions. The null hypothesis, we've talked about it in a couple contexts now, so it's time to give it a definition. The null hypothesis, H0, is the contention that the treatment makes no difference. That if you report any difference in your study, it's only because of routine sample-to-sample variation. The alternative hypothesis is the claim that the treatment makes some genuine difference, that there's a genuine phenomenon here, and the numbers reported from the sample reflect that difference. Not that the sample numbers are right, not that the sample number is the population number, but rather that the sample number varies from the nominal, 0.5 in the two examples I just did. The sample number varies from the nominal because there's a genuine phenomenon happening. Usually, 99.9% of the time, what's happening is that we suspect HA is the correct, is true. And usually we argue by providing evidence against H0. So we get the H0 people to change their mind, and again, the technical jargon is we seek to reject H0. Specifically, we will assume for the sake of argument that H0 is true, and then we find the chance that our statistic, a statistic as extreme or more extreme than the one we found, and that chance is called the p-value. If the p-value is small, then it's hard to believe H0. That is, a small p-value provides strong evidence against H0. Usually that's what an experimenter wants, strong evidence against H0. Often there's some criteria for the p-value. The criteria is denoted alpha, that's the Greek letter alpha. If the p-value is less than alpha, then the test is called statistically significant at level alpha. If the p-value is less than alpha, then the test is statistically significant at level alpha. I had a little trouble getting it out. We saw that in the previous slide where the doctor said, in our field, said to the people in the seats, in our field, there's a general agreement that experiments with a p-value less than 5%. So the doctor's talking about alpha equals 5%, alpha equals 0.5. Okay, so often there's some criteria that people in a field have agreed on, and it's denoted alpha. A p-value less than alpha, and then we say the test is statistically significant at level alpha. And a couple notes, and then we'll call that a day for the video. So there's two possible outcomes for a hypothesis test. You could reject H0 or you could fail to reject H0. Never do you accept H0. You either reject H0, that means you change the minds of the folks in the seats, or you fail to reject H0. That means they say, okay, you failed to persuade us. You're going to have to provide stronger evidence than that. We're still not convinced that you're right. And the value of the criteria, alpha, depends on your field. In many social science and psychology fields, it's alpha equals 5%, alpha equals 0.5. For example, if you're an education researcher and then the journal you want to publish in may have a statement inside the front cover that says, we use a significance level of 0.5, don't send us a paper unless the p-value is less than 0.5, you're just going to go in the trash. In contrast, if you work in the field of manufacturing artificial hearts, then of course they're going to require quite strict standards. So if you say, we're positive our artificial heart lasts for 10 years, they're going to require a very strict alpha, maybe alpha equals 0.00001, for example. I worked for a while on some space materials, and same sort of thing. It costs a lot of money to send this stuff into space. So if you want to make a claim that this material will last at least 12 years, you've got to make it with great confidence, and so you're required to have a very strict alpha. And then the last point is, conceptually we write down the hypotheses before we gather the data, and likewise conceptually we agree on alpha before the study. And we'll see that when we talk about things later. Okay, a lot of material to do, and we've broken the videos into 3 different parts just to try to make it more graspable. All right, so we'll see you for the next one.